What is a black hole, and how is it formed? There are only a handful of natural phenomena that were first predicted analytically and then observed later. Black holes are one of those exceptional examples. In the 1780s, natural philosopher John Michell observed that the gravitational attraction of a star that was sufficiently dense may be so strong that even light that was generated by the star would be unable to escape its hold. This was the first time that their existence was anticipated. The astronomers were relieved when they made the finding in Cygnus because if they hadn't made the discovery, they would have been considered insane for believing in an object that is so enormous that it is invisible. Because Michel's star does not produce any light, it would not appear to be like this, but rather, it might be something similar to this. Black holes are named black holes because that is exactly what they are, a black nothingness in space. This is the reason why they are called black holes. We need to take a look at the difficult childhood that a star had to comprehend why they would ultimately become so reclusive. A star is formed when gravity drives a massive volume of hydrogen gas to collapse in on itself, resulting in the formation of a star. Because of this compression, the temperature of the gas rises, which in turn causes the atoms in the gas to violently smash with one another, to the point where the hydrogen atoms no longer collide and ricochet, but instead merge to produce helium atoms. These collisions continue to heat the gas with increasing intensity. When compared to the combined mass of two hydrogen atoms, the mass of a helium atom is significantly lower. The remaining mass is released as energy, the magnitude of which is determined by Einstein's equation E equals mc squared. This equation describes how stars form. If two atoms are merging, the amount of energy that is released may be relatively low. However, if there are billions and billions of them, the cumulative release is enormous. It is possible to reproduce the same process that causes a star to shine within a destructive hydrogen bomb, but in a controlled manner. The star's expansion, which is caused by the explosion, must counteract the compression that is caused by its gravity for it to continue existing. However, the star will eventually exhaust its store of fuel. All of the hydrogens have been converted into helium, and all of the helium has been converted into carbon, and so on until iron is finally produced through the process of synthesis. Because iron is unable to fuse any further, the star is now packed with a great deal of heavy elements. The star starts to cool down since it no longer has any fuel to burn, and because it does not have any heat to fight the compression, it starts to contract over time. Dwarves of the white race. During his journey from India to England in 1928, Chandrasekhar realized that a star might continue to exist if the contraction caused by gravity is counteracted by the repulsive forces that exist between the stuff that is grouped close together. We now refer to these types of stars as white dwarfs, because all of the mass is contained within a sphere that is just 1,000 miles in diameter. These are dense to the extent of hundreds of tons per cubic inch. However, if the star were to be any denser, its gravity would be strong enough to overcome even the forces that are causing the electrons to repel one another. Based on his calculations, he determined that a cool star with a mass that is 1.5 times that of the Sun would experience further contraction. Nevertheless, it can maintain its existence by counteracting the pull of gravity by utilizing the repulsive forces that exist between its neutrons and protons. As a result, This type of star is referred to as a neutron star because all of the mass will be contained within a sphere that is only 20 miles in diameter. These are millions of tons per cubic inch dense. What would happen, however, if a star were to have an even higher density? When Chandrasekhar presented his findings to Arthur Eddington, an astronomer, after he had arrived in England, Eddington was unable to accept the possibility that a star could grow infinitely dense. He refused to accept the possibility that a star of the sun's magnitude might collapse to a certain point. Stephen Hawking and Roger Penrose predicted in the 1960s that an even denser star would collapse into a point of infinite density and as a result, space-time curvature. They predicted that this point would be the point at which all of the known rules of physics would have broken down. The singularity is the name given to the point, the singularity. Because a singularity twists the space-time around it to such an extreme degree, the star transforms into a black hole. This means that any light that falls into the pit is trapped there for all of eternity. Nothing can get away from it. This barrier, which marks the beginning of the pit, is referred to as the event horizon of the black hole. It is of the utmost importance to be aware of the fact that black holes do not suction everything like a vacuum cleaner in the universe. What would happen if a big or supermassive black hole with the mass of the sun were to replace it? We would continue to revolve without being disturbed. However, survival would not be a given in this scenario. Therefore, we have built a mathematically valid model of a black hole. But the question remains, how is it possible to obtain evidence that a black hole exists? According to Hawking, how is it possible to locate a black cat in a completely dark room? The next thing we did was direct our telescope in the direction of the constellation Cygnus. In terms of the intensity of X-rays that may be observed from Earth, Cygnus X1 is among the most powerful sources. Astronomers came to the conclusion that matter from the revolving star was thrown away into orbit around evidence, which was its companion that was not visible to the viewer. As a result of the revolution, it became extremely hot, to the point where it emitted X-rays. The entity that was not visible, on the other hand, did not necessarily have to be a black hole. It was just as possible to be a big star that was just too dim to be seen. Nevertheless, astronomers were able to determine the mass of the object to be 6 times that of the sun by utilizing their understanding of the mechanics of the star's orbit through space. The object couldn't be a neutron star or a white dwarf due to its huge size. Even though we do not have any direct proof because of the withdrawn nature of Cygnus X1, we do have a great deal of indirect data that implies that it is most certainly a black hole. During his lifetime, Stephen Hawking held the belief that the universe is filled with black holes. He made the daring assumption that the number of black holes is bigger than the number of stars that are visible to the human eye. There must have been millions of stars that have used up their fuel throughout the billions of years that our universe has been around. It is believed that the center of our galaxy, as well as potentially the center of every galaxy in existence, contains supermassive black holes that have a mass that is billions of times greater than that of the sun. What is even more astounding is the fact that Hawking, who went on to occupy the renowned Lagrangian chair at Cambridge, which Newton had previously held, demonstrated that black holes are not as dark as they appear to be. It was discovered by him that they give off extremely minute amounts of radiation, which we now refer to as Hawking radiation. In the end, a black hole will disappear, but it will take 1 billion and billions of years for it to entirely evaporate. Black holes emit particles and finally disappear. Last but not least, a singularity is the occurrence that has the highest notoriety throughout the universe. No one knows what the enigma is that lies at the bottom of the pit, but it appears to unite the two last elements of mathematical theory. Its features on a broad scale are related to the classical theory of general relativity, yet its point size is related to the quantum mechanics described at the microscopic level. The theory of everything refers to the combination of all of these concepts. Over more than 60 years, nobody, not even Albert Einstein, has been able to get their hands on it. Final thoughts. It will incorporate every tiny discovery that man has made throughout his search for certainty. The theory of everything will undoubtedly be the most significant achievement of human reason since the beginning of time. So match the frequency of your dream reality, and you will experience what you want. See you in the future video, and thanks for watching!